Hello everyone, and welcome to today's presentation on remote sensing. I'm excited to have you here. Today, we'll explore the concept and principles behind remote sensing, giving you a clear understanding of how it works and its applications. We'll cover the basics, the technology involved, and why it's such a powerful tool in various fields. So, let's get started and dive into the fascinating world of remote sensing. Today, I want to introduce the concept of remote sensing, which is a fascinating blend of art and science. At its core, it's about obtaining information about an object or a phenomenon without having to be physically in contact with it. This means we can study something from afar, which is especially useful when direct contact isn't possible or practical. The definition by Jensen in 2000 really captures this idea well. He describes it as the art and science of obtaining information about an object without being in direct contact with the object. In more technical terms, remote sensing involves collecting data through devices or sensors that are not in physical contact with the target. Then, we analyze this data to derive meaningful information about the object or phenomenon we're investigating. This approach is fundamental in many fields, from environmental monitoring to urban planning, because it allows us to observe large or inaccessible areas efficiently and effectively. Throughout this presentation, we'll explore how remote sensing fits into the bigger picture of geographic information systems and how it helps us understand our world better. Let's delve into the principle of remote sensing. Essentially, every object in the environment interacts with electromagnetic energy in a unique way. When sunlight or other energy hits an object, part of that energy is reflected or scattered depending on the object's physical properties. This means that different materials will reflect different amounts of energy. Now, what's really interesting is that this reflection pattern isn't random. It varies across different wavelengths of light. This variation follows a specific pattern called a spectral signature, which is characteristic of each object. By properly interpreting these spectral signatures, we can identify and differentiate objects from a distance. This core idea underpins how remote sensing allows us to analyze Earth's surface without direct contact, making it a powerful tool for various applications. Let's walk through the process of remote sensing. It all begins with radiation and the atmosphere, which is the first step. Here, the Earth's atmosphere interacts with incoming energy, affecting how much radiation actually reaches the Earth's surface. Next, we have the interaction with the target, where the energy from the sun or other sources hits the Earth's surface and interacts with different objects or land types. Following that, the energy recorded and converted by the sensor comes into play. Sensors on satellites or aircraft detect this energy, capturing data that can be analyzed later. Then, we move to reception and processing, where the signals collected are received and processed to prepare them for interpretation. Finally, the last step is interpretation and analysis. This is where we analyze the processed data to extract meaningful information, such as land use, vegetation health, or urban development. Each step in this process is crucial for understanding what remote sensing can reveal about our planet. It's a systematic flow that transforms energy from the environment into valuable insights we can use for various applications. Let's take a closer look at the electromagnetic spectrum, or EMS for short. This spectrum includes a wide range of electromagnetic waves, each with different properties and uses. For example, we have TV and radio waves, which are used for broadcasting signals we rely on every day. Then there are X-rays, which help us see inside our bodies at the doctor's office. Microwave radiation is what heats our food in the microwave oven. Infrared waves are associated with heat, like the warmth you feel from the sun or a fire. Ultraviolet light is what causes sunburns, but it also helps our bodies produce vitamin D and finally, gamma rays, which are incredibly powerful and are used in medical treatments and also observed in space phenomena. Now, all these different types of waves are classified based on their wavelength, meaning the length of the wave. This classification helps us understand their behavior, their energy levels, and how they interact with matter. It's important to see that all these waves together form what we call electromagnetic radiation. This radiation is all around us, and understanding its spectrum helps us grasp how different types of energy are transmitted and utilized in various applications. So the key point here is that the electromagnetic spectrum is a continuous range, but we categorize it into these different types based on wavelength, which is crucial for understanding their properties and uses. This concept ties directly into our overall theme of exploring how electromagnetic waves influence our daily lives and the technology we depend on. Electromagnetic radiation is a fascinating form of energy that's constantly moving and changing. It's capable of propagating through a vacuum, which means it doesn't need a medium like air or water to travel. And interestingly, we only become aware of this energy when it interacts with matter, such as our eyes detecting visible light or instruments sensing other wavelengths. Now, if we look at all the electromagnetic waves together, they form a continuous spectrum, ordered by their frequency and wavelength. This spectrum includes everything from radio waves to gamma rays, with each type having its own unique properties. The Sun, the Earth, and other celestial bodies all radiate electromagnetic energy, but the wavelengths they emit vary greatly. Some wavelengths are visible to us, like sunlight, while others are invisible but still critical, like X-rays or radio waves. And this radiation travels through space at the incredible speed of light, taking the shape of sinusoidal waves. Think of them as smooth, repeating oscillations. Understanding electromagnetic radiation helps us grasp how energy moves across the universe and interacts with matter, which is a key theme in our exploration of how energy transfer shapes our world. Let's take a closer look at the properties of EMR, or electromagnetic radiation. First, one of the most fundamental aspects is wavelength. This is essentially the distance between successive peaks of the wave, and it determines many of the wave's characteristics. Shorter wavelengths, like X-rays, have higher energy, while longer wavelengths, like radio waves, have lower energy. Another key property is frequency, which is how many wave cycles pass a point per second. Frequency and wavelength are inversely related, meaning, as one gets shorter, the other gets longer. This relationship is crucial because it influences how the radiation interacts with matter. Next, we have energy, which depends directly on frequency. Higher frequency waves carry more energy, which explains why X-rays can penetrate tissues more effectively than visible light. Intensity is also important. It refers to the amount of energy the wave carries per unit area. Think of it as how strong the wave feels, impacting how much energy is delivered to a target area. Finally, the properties of EMR are interconnected and form the basis for understanding how different types of radiation are used in various applications, from medical imaging to communication technologies. Recognizing these properties helps us grasp why certain wavelengths are suitable for specific purposes and how EMR interacts with matter in diverse contexts. Let's start with wave theory, which describes electromagnetic radiation as waves with specific wavelengths and frequencies. This helps us understand how energy propagates through space. Moving on to quantum theory, which is essential because it introduces the idea that energy is quantized, especially at smaller scales, and explains phenomena that classical theories can't. Next is Stefan Boltzmann's law, a fundamental principle that states the total energy emitted by a blackbody is proportional to the fourth power of its temperature, giving us a way to calculate the energy output based on temperature alone. Then, we have Planck's radiation law, which was groundbreaking because it accurately describes the spectral distribution of blackbody radiation, bridging the gap between classical physics and quantum mechanics. Following that is Wien's displacement law, which tells us that the wavelength at which the radiation peak shifts to shorter wavelengths as the temperature increases, so hotter objects glow with bluer light. Lastly, I want to touch on the concepts of electromagnetic radiation, or EMR, which encompasses all forms of radiation, visible light, radio waves, X-rays, and how understanding these concepts helps us interpret the universe, from the cosmic microwave background to stellar spectra. All these theories and laws are interconnected, forming the foundation for our understanding of how energy interacts with matter across the electromagnetic spectrum. Let's explore the key components of electromagnetic radiation. First, we have the electric field, which we denote as E, and the magnetic field, represented as M. These two fields are fundamental to understanding how electromagnetic waves behave. Back in the 1860s, James Clerk Maxwell made groundbreaking contributions by describing the characteristics of electromagnetic radiation, or EMR. He showed that EMR travels at the speed of light, which is approximately 3 × 10⁸ Now, electromagnetic radiation is essentially a continuous transverse wave, meaning the electric and magnetic fields oscillate perpendicular to the direction of wave propagation. These oscillations are vital. They create the wave's structure and energy transfer. The radiation is characterized mainly by two properties: frequency and wavelength. The frequency, denoted as nu, tells us how often the wave oscillates per second, while the wavelength, lambda, is the distance between successive peaks. The relationship between these properties and the wave's speed is captured by the equation c equals nu times lambda. Here, c is the speed of light, which, as I mentioned, is 3 × 10⁸ This equation helps us understand how changing the frequency affects the wavelength, and vice versa. This wave theory is fundamental because it explains how electromagnetic waves propagate through space, carrying energy without needing a medium. It's a core concept that underpins much of the electromagnetic spectrum and its applications. So, in summary, electromagnetic radiation consists of oscillating electric and magnetic fields traveling together at the speed of light, characterized primarily by their frequency and wavelength, which are interconnected through this wave equation. This understanding is essential as we delve deeper into how these waves interact with matter and their role in various technologies. Now let's talk about two important concepts when it comes to waves. First, frequency. This is essentially how many wave cycles pass a fixed point in a given amount of time. Think of it as how often the wave repeats itself over a period. The higher the frequency, the more wave cycles occur per second. Next, we have wavelength. This refers to the length of one complete wave cycle. You can picture it as the distance between two successive peaks of the wave. Wavelength is a key factor because it helps us understand the wave's energy and how it interacts with the environment. Both of these characteristics, frequency and wavelength, are fundamental in understanding electromagnetic radiation, or EMR. They influence properties like the wave's energy, how it travels, and how it affects matter. As we explore EMR further, keep in mind that these two parameters are central to describing and understanding its behavior. Let's talk about how electromagnetic radiation interacts with matter. EMR isn't just a continuous wave. It's actually made up of many tiny units called photons or quanta. These photons are like discrete packets of energy. Now, the energy of each quantum can be calculated using this simple equation. Q equals h times upsilon. Here, Q is the energy measured in joules. H is Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds, and upsilon represents the frequency of the radiation. What's really interesting is how this relates to the wave model of M radiation. We can connect the quantum concept to the wave model with this other equation. Q equals hc divided by lambda. In this case, h is still Planck's constant, c is the speed of light, and lambda is the wavelength. Essentially, this shows us that the energy of a photon is inversely proportional to its wavelength, meaning shorter wavelengths have higher energy. This quantum theory helps us understand phenomena that the wave model alone can't explain, like the photoelectric effect. It's a fundamental idea that links the particle-like behavior of light with its wave properties, which is key to our overall understanding of electromagnetic radiation and its interaction with matter. The longer the wavelength, the lower its energy content. This is a fundamental concept in quantum theory. Essentially, when we talk about waves, a longer wavelength means the wave oscillates more slowly. And in the world of quantum physics, this relates directly to the energy of a quantum. The key point here is that the energy of a quantum is inversely proportional to its wavelength. So, as the wavelength gets longer, the energy decreases. Conversely, shorter wavelengths mean higher energy. This relationship helps us understand many phenomena at the atomic and subatomic level. It also ties into the broader theme of how energy and waves are interconnected in quantum mechanics. Recognizing this inverse relationship is crucial for grasping how particles behave at a microscopic scale. All matter at temperatures above absolute zero, which is minus 273 degrees Celsius, continually emits electromagnetic radiation. So, anything with a temperature above this point is constantly radiating energy into the environment. Just like the sun, terrestrial objects, meaning things on Earth, are also sources of radiation. However, the amount and the spectral composition of this radiation are different from that of the sun. The sun emits a broad spectrum of radiation, while objects on Earth emit radiation based on their temperature, which tends to be in the infrared range. Now, the key point here is that the amount of energy an object radiates can be described mathematically. This is where the Stefan-Boltzmann law comes into play. The law states that the total radiant energy emitted per unit area of a surface, which we call m, is proportional to the fourth power of its absolute temperature, T. Mathematically, we write this as m equals sigma times T to the fourth power. Here, sigma is the Stefan-Boltzmann constant, which is approximately 5.6697 times 10 to the minus 8 watts per square meter per Kelvin to the fourth. And T is the absolute temperature in Kelvin of the emitting material. So what does this tell us? Essentially, as the temperature of an object increases, the amount of energy it radiates increases dramatically, since it's proportional to T to the fourth power. This law helps us understand and quantify the radiative energy exchange between objects, which is fundamental in fields like climate science, astrophysics, and thermal engineering. Connecting this to the overall theme, understanding how objects emit radiation allows us to better grasp energy balance in natural and engineered systems, and helps us develop more accurate models of heat transfer and climate processes. Let's take a closer look at this equation, which is known as the Planck radiation law. It describes the intensity of radiation emitted by a black body per unit surface area into a specific direction, or solid angle, depending on the wavelength and temperature. On the left side, E, lambda T, represents the spectral radiance, essentially how much energy is emitted at a particular wavelength lambda and temperature T. The right side of the equation involves several constants: H, which is Planck's constant, K, Boltzmann's constant, and C, the speed of light. These constants are fundamental in physics and help define the behavior of black body radiation. The equation has two main parts: the numerator, 2hc2 divided by lambda 5, which sets the scale of the emission, and the exponential term, ehc/lambda t minus 1, which accounts for the distribution of energy across different wavelengths at a given temperature. It's crucial to understand that this law is the primary governing principle for black body radiation. It explains how objects at a certain temperature emit radiation across the spectrum, from infrared to visible light, depending on their temperature. This law forms the foundation for understanding many astrophysical phenomena and the behavior of thermal radiation in various scientific fields. It connects the microscopic quantum effects to macroscopic observations, which is really fascinating when you think about how it all ties together. Now, let's look at the wavelength distribution of radiated heat energy from a black body at any given temperature. What's interesting here is that this distribution has essentially the same shape regardless of the temperature. The main difference is that each wavelength shifts along the graph depending on the temperature. This means that as the temperature changes, the peak of the radiation curve moves, but the overall shape stays consistent. The wavelength at which this maximum emission occurs is very important and is related to temperature through what's known as Wien's law. Wien's law states that the dominant wavelength, or the wavelength at which the blackbody radiates the most energy, is inversely proportional to the temperature. The formula is lambda equals a divided by T, where lambda is the wavelength of maximum spectral radiant excitance in micrometers. A is Wien's displacement constant, which is 2898 millimeters Kelvin, and T is the temperature in Kelvin. This law is crucial because it links the color or wavelength of radiation to temperature, helping us understand how objects emit heat at different temperatures. It ties directly into our overall theme of thermal radiation and how temperature influences the energy distribution of blackbody radiation. Let's take a look at this blackbody radiation curve. As you can see, it shows how a perfect black body emits radiation at different wavelengths. One key point here is the wavelength of 9.7 micrometers, which is significant because it corresponds roughly to Earth's thermal radiation. This is why Earth emits primarily in the infrared, around this wavelength. Now compare that to an incandescent lamp. Such lamps emit a broad spectrum of radiation, including visible light and infrared, because they are heated objects radiating energy across many wavelengths. This connection is important because it highlights how objects at different temperatures emit different spectra. Earth, being much cooler than a lamp filament, emits mostly infrared radiation at around 9.7 micrometers. Understanding these curves helps us grasp how thermal radiation depends on temperature, which is a core idea in the study of black-body radiation and thermal emission. This understanding is fundamental to our overall theme of how objects radiate energy based on their temperature. Now, let's take a closer look at the electromagnetic energy interactions involved in remote sensing. When energy from the sun is being remotely sensed, it first originates from atomic particles at the source, which is the sun itself. This energy then travels through the vacuum of space at the incredible speed of light, covering vast distances to reach Earth. Once it arrives in our atmosphere, it interacts with the atmospheric particles, which can scatter or absorb some of that energy. After passing through the atmosphere, the energy reaches the Earth's surface, where it interacts with various features, like land, water, or vegetation, each affecting the energy differently. Then, the energy can interact again with the atmosphere as it leaves the surface, potentially scattering or absorbing further. Finally, this energy makes its way to our remote sensors. Here, it interacts with optical systems, filters, emulsions, or detectors, which are designed to capture and measure this energy accurately. Understanding these interactions is crucial because they influence the data we collect and, ultimately, how we interpret that data. Recognizing how energy is modified at each stage helps us better understand the information we're analyzing and ensures more accurate remote sensing applications. Now, on this final slide, we're focusing on electromagnetic energy interactions, and specifically, the role of the Solar and Heliospheric Observatory, or SOHO for short. SOHO is a vital tool that helps us understand the sun's behavior and its influence on the solar system. What you see here is an image of the sun, obtained on September 14, 1999. This snapshot highlights the incredible detail and data SOHO can provide, helping scientists track solar activity like sunspots, solar flares, and coronal mass ejections. These phenomena are all different ways the sun interacts with electromagnetic energy, sending energy across space that can affect everything from satellite communications to power grids here on Earth. Understanding these interactions is crucial because they influence space weather, which in turn impacts our technology-dependent society. So, by studying tools like SOHO, we're gaining a better grasp of how electromagnetic energy from the sun propagates and interacts with the solar system, reinforcing the overall theme of energy transfer and space weather dynamics.